Hello, this will be the first video on this channel, and it will pertain to complex numbers. Now, before we get to I should first explain what they are. In essence, complex numbers, if you're watching this, are probably familiar with the real numbers. The real numbers are on this axis. 0, 1, 2, 3, -1, and all the numbers in between. Now, perpendicular to this, so as to indicate that vector-wise there is no correlation between them, they can't interfere with each other, there are the complex numbers, which, much like the real numbers, start from 0, 1, 2, -1, -2, so on and so forth, and all the numbers in between. Now, these numbers, they do not interact, at least addition-wise. What does this mean for us? For example, if, once again on the complex plane, with this being the real numbers indicated by r, the axis, and this being the imaginary numbers, we may have a number that has components from both axes. That is, it has elements of both axes, and these elements do not interfere with each other, at least addition-wise. Although this being said, they may interfere when multiplying, but we will save this for another day. In essence, if we have a point here, say 1, 1, this will correspond to the number 1 plus 1i, wherein the I here indicates that it is an element from this axis. And that is basically the basics of the concept. Now, it may seem that this has no practical applications. However, if you, in the future, or if you're currently studying electricity, you will come to see that, indeed, imaginary numbers, as indicated... I should mention that complex numbers have two parts, imaginary and real. So when I said complex numbers initially, I had forgotten to say this, yet now I say this. This would be the imaginary part, this would be the real part, the axes rather. In essence, if you study electricity or the such, you will come to encounter, through current and other matters, that sometimes considerations have to be made for imaginary numbers. Now, let's get to how these behave and how we can describe them. But before that, let's do another example. For example, if we have this point corresponding to 2, 1, and this point on the complex plane corresponding to, let us say, -1. Oh, I should not put that there. Sorry. -1, -1. And we were to add these up. Well, before that, let's see, this is point A and this is point B. Point A is 1 plus 2i. The 1 comes from the... sorry, I am mistaken. It is... Point A is, this being the imaginary axis and this being the real, 2 plus I, or rather 1i. But this is the same thing, in that the 2 comes from the real axis and the 1 comes from the imaginary axis. Point B, on the other hand, corresponds to -1, stemming from the imaginary real axis, plus, or rather minus, -i. But we will just do minus I, stemming from the imaginary axis. Now, with complex numbers, we can add these up. However, we must add them up component-wise. For example, if we were to add a plus b, we would have to do this component-wise. So before we write this out, we would have the following. In the real part, a has a magnitude of 2, and b has a magnitude of -1. So plus -1. The real component of the sum of these imaginary numbers would thus be 1, as 2 plus -1 is 1. The imaginary component, on the other hand, would correspond to 1 for A plus -1 for B, as is demonstrated here and here. This would correspond to 0. So, in essence, we would write A plus B as first the sum of the real parts, which is 1, plus the imaginary part, which would be 0i, or just 1. Now, the important thing to take away from this is that you can add up complex numbers, but you have to deal with them component-wise. You cannot add the imaginary part to the real part, and they do not respectively interfere with one another. Sorry, I will take a quick drink of water. Now, as you can see, we can essentially, that is rather premature. As said before, the complex numbers may be represented on a plane. Now, say we have 2 on the real axis, and once again, perhaps 1 on the imaginary axis. Now, this would correspond to such an imaginary number. And I should mention that imaginary numbers, regarding this graph as well, may be indicated by points, but may also be indicated using vectors, from the origin to the points. Now, regarding this current diagram here, as you can see, there is a clear ratio between the, between the real parts and the imaginary parts. Now, regarding this matter, if I can grab my calculator, we can, in essence, represent the imaginary number using this angle. Let us call this theta. Now, the ratio between the imaginary side being this side and the real side being this side would be tan theta. And in this case, it is 1 to 2. So in order to find this angle, we take the inverse trig function from both sides as follows. And we get, I apologize, I'm inputting this into my calculator, approximately 0.464 radians. And it should be mentioned that radians, you do not need to indicate the unit. However, I will do so. Now, we have established that there is, of course, the angle. However, we can also see that we can take the, we can take the cosine of this angle, cosine of 0.464, though I would recommend you do not use the rounded figure. And you will receive approximately 0.89. Now, as it pertains to this, I believe this would essentially be the horizontal axis, or the real part, if this hypotenuse was a unit vector, so it were 1. And respectively, sine of 0.464 being roughly equal to 0.448 would be the following side, the opposite side of the angle, this being theta once again. However, as you can see, though our angles are proportionally 1 over 2, they themselves clearly are not 1 for the opposite angle and 2 for the adjacent angle. And here is wherein we solve this problem. As you can see, the hypotenuse is 1. And these two triangles are similar. As such, we will find out the factor by which they are similar. Indeed, to do this, we will need to see the hypotenuse of the initial triangle. And we can calculate this using Pythagorean theorem. We take the first side, and we add it to the second side. Of course, we square these initially, and this becomes 5. And further, we take the root of the whole equation. So we get that the hypotenuse of the initial triangle is root 5. With this information, we know that the triangles are in the ratio of root 5 to 1. So, if we are to multiply the sine of 0.464 by root 5, and similarly the cosine of 0.464 by root 5, we will, in turn, get 1 and 2 respectively. And herein we arrive to our initial equation. Now, how do we use this to represent imaginary numbers, or rather complex numbers, in a different way? Well, there is a notation called cis, which is a mixture of cosine and sine. Essentially, we take the magnitude of the complex number, that is the magnitude of the vector, and we multiply it by the sine of by theta, and we add it to the cosine of theta times I. The reason we do times I is because, I apologize. It appears that it is or rather, I had mistakenly said the I goes with the cosine, yet it goes with the sine. We can see this as it is the vertical axis, as you can, if I can zoom in, as you can see here, that consists of I. Therefore, sine, consisting of the vertical parts, will correspond to this, and therefore we will multiply it by I in order to give it the proper dimension, or rather the proper component. And once again, cosine corresponds to the horizontal axis. As such, we will not give it I, so that it represents the real numbers. And therefore, this becomes equivalent, or rather this statement is equivalent when theta is 0.464 to, if I can remember, 2 plus I. Now, interestingly enough, we once again come back to cis. Instead of writing I sine plus cos theta, we may write root 5 times cis theta, which is once again equal to our complex number. And remember, always it is R standing for the magnitude times cis theta. That is how you represent complex numbers. I apologize for the informality of this lesson. There is yet another topic, however, before we conclude. Now that we've established what cis is and what imaginary numbers are, we will regard two critical operations. First being the conjugate of the imaginary number. This is supposed to be a star. And the modulo modulus of the imaginary numbers. Now, the modulus is essentially the magnitude of the imaginary number vector. If we return back here, we saw that you simply take the real component and the imaginary component and imagine them as a part of a 90-degree angle and find the hypotenuse. This would correspond to the modulus, indicated by the name of the imaginary number with a line atop it. Now, the conjugate, however, is more interesting. The conjugate is, the conjugate of an imaginary number is, in essence, identical to itself, only the difference being that it is flipped in the horizontal, or rather over the x-axis. So if this is our z, being our imaginary number, this would be the conjugate of z. Respectively, if this is our z, our imaginary number, this would be the conjugate of z. Now it ought to be mentioned in both cases that this angle is equal to this angle, and this angle is equal to this angle. By this angle, I refer to the angle the vector makes with the, or rather the acute angle, or the minimal angle the vector makes with the horizontal axis. In essence, this can be represented through a negation of the sign of the complex number. So for example, if we have the number 3 plus 2i being equal to z, the conjugate of z would be equal to 3 minus 2i. Respectively, if we have z is equal to 4 minus 5i, the conjugate of z becomes 4 plus 5i. And once again, I apologize for the informality of the lesson. This was my first attempt, and I hope I've taught you well, or rather I have taught you something. Thank you very much for listening. I hope you pursue your academics well and have enjoyed it thus far. Thank you.